Okay, so now what we're going to do is we're going to determine what the acid dissociation constant for bromocresol green is. This is sort of the end point here. So referring back to the equation, I'm back here in the lab procedure. If you look at this equation right here, this is essentially the Henderson-Hasselbalch equation, but it's been rearranged. So we're going to consider the Henderson-Hasselbalch equation for the bromocresol green. The bromocresol green has two forms that we're concerned with. One is doubly ionized, meaning that two hydrogen ions have been removed. So we'll call that B2 minus. The acidic form actually is HB negative. It has one hydrogen already off, okay? So that's the log of the ratio of the conjugate base to the weak acid. So that's part of the Henderson-Hasselbalch equation. Another part of the Henderson-Hasselbalch equation is the pH, right? And then you got the pKa, right? But what they've done in this form of the equation is they've left the log of the Ka on one side, on the right side of the equation. Okay, so it's not pKa because minus log of the Ka is pKa. It's just log of the Ka. Now, again, I won't go through this, but it turns out that this ratio, the conjugate base to the weak acid, is related to the absorbance values that you measured. So you measured different absorbances when you add different amounts of the acetic acid. What you're doing is you're changing this ratio every time you add more acetic acid. You're giving it more acid and less base. And then, you have the absorbance, the maximum absorbance of the base is A2, and then the absorbance of the acid form at that same wavelength is A1. Okay, so this ratio here can be shown to be equal to this ratio, which is connected to the Henderson-Hasselbalch. So all we have to do is do a graph of this versus pH, and this would be the y-intercept, right? So this would be x. So this would be like y equals mx, where m is the slope, and the slope is 1. pH is x, plus log of k. Log of k would be the y-intercept, okay? So pretty straightforward there. So that's what we're going to do. We're going to do a graph. Now, the pH is going to be on the x-axis. So what I'm going to do is I'm going to put the pH over here, and then I'm going to put the log of the absorbance. So I'll just write here, just as a shorthand notation, the log of the absorbance, okay? But the absorbance we're talking about is actually this ratio here. So I'm just using that as an identifier. So equal sign this one. So I'm just going to go ahead and what I'm doing is I'm just essentially copying these numbers over. But again, I'm doing it equal sign, then clicking on the cell so that in case I change these values in the future, it'll automatically change down here. Okay. Same thing here. I'm just going to pick this one right here and autofill. Okay. Looks pretty good. These values are the same as are up here, down here, okay? All right, so we're good. So now let's go ahead and do a graph. So I'm gonna pick this, and I'm gonna go to insert a chart, and we don't want a line graph. This is automatically, this is defaulting to a line graph. We don't want that. We want a chart type. We want to pick what's called a scatter. Okay, so we got our scatter graph right there. And then we want to show a couple of things, right? We want to show the equation, all right? And we want to show the R squared value. So if I come over to customize, well, I think it's actually in setup. So let's come over here. Scatter chart. Oh, for some reason, it's not showing us the... Oh, let's come, sorry, my mistake. Click on that. You got to click on one of the points, and then these other options pop up, okay? So trend line, we want the trend line. It's probably a good idea to show R squared. It's pretty high. R squared is 0.997. And so the higher R squared is to 1, the closer to 1 it is, the better. That's pretty close to 1. And then the only thing else we want to do is our custom label. We want to make the equation. We need that equation, okay? So there we go. So there's our equation. Now, in many of the graphs that we've done in other experiments, we wanted the slope. But in this case, we just want the y-intercept. So the y-intercept is negative 3.59, right? It's mx plus b is the equation for a generalized line. So m is the slope, x is the pH, plus negative 3.59. Negative 3.59 is the y-intercept. So I'm going to type in here y-intercept is minus 3.59. Okay. Now, coming back to our discussion here, the log of the k is the y-intercept. That's not k, it's the log of the k. So if we want to get rid of the log, we have to do 10 to the x. So the k, or Ka, equilibrium constant, would be 10 raised to the y-intercept, the anti-log, we might call that. A lot of sig figs, it's in bad notation. Let's put it in scientific notation and then cut down on the number of sig figs. Oops, that's a little too much. Okay, probably you're really justified in having 2 sig figs, so I'll come back here and make it just 2. And there we go, 2.6 times net 10 to the minus 4 is our result. So what we're claiming now out of all of this, and this is very often how the physical sciences operate. You do an experiment, you get your results from the experiment, you do a lot of processing of data, a lot of calculations, you do a graph out of that, and then you grab a parameter out of the graph. In this case, the y-intercept was the parameter, and that's what we needed in order to find out what Ka was. So your final answer when you do these calculations should have a graph with linear regression, and you should have a y-intercept, and then you should do the final calculation, which is to turn the y-intercept into the acid dissociation constant of bromocresol green. Okay, so again, you'll be using your own data, of course. I just made these numbers up for you just to sort of see how to go through them, but that's how we would get our results.